Okay, so let's start. In the last lecture, we had seen that the two sequential systems, mealy and more, that we had discussed are, although very general in nature, they are inadequate for modeling a variety of sequential digital systems. And we had seen this particular example. We had said that let's suppose we want to design a system in which we have 4-bit inputs, two of them, x and y. And what we would like to do is add up the two inputs, x plus y, output it at z1, and subtract x minus y and output it at z2. And even for this very simple system, if we try to model it as a mealy or more machine, things get complicated. For example, we can very easily see that the system we could perhaps implement in this particular form. That x and y that you see here, we read x into register R1, we read y into register R2. This is an adder subtractor block, and depending on the select value here, let's say if it is 0, it adds, if it is 1, it subtracts, and then the output you put it in these registers here, R3 and R4 here. So we can easily implement this functionality that you see here in a form of a block diagram like this. Now, if we try to think of this block diagram in terms of let's say a mealy or a more machine, then note we had seen earlier mealy and a more machine has state memory combinational logic blocks, right? And if we look at these 4 storage elements that are there, each one of them has 4 flip-flops, and so you have 4 here, you have 16 of them, and so the number of possible states are huge. If you start to think about how many states are possible in a system like this, each one of those 4 bits can be anything from 0000 to 1111, and similarly of this one, and so on and so forth. So the possible number of states of this particular system are very large. If we think of states in terms of the storage that is there, the possible number of states are very large, and obviously it's ridiculous to model this in the form of saying how many states are there and how do I go from one state to the next. That's not the right way of modeling such a system here. So what we need is a different way, a slightly more general method of modeling the digital system, which encompasses within it the finite state machine that we talked about. And this is the view that we model our digital system as consisting of 2 major blocks. One of them is the data path, and the other one of them is the controller. So the idea is that the data comes into my system, and the data path processes it. And the processing of the data path, what occurs in the data path is a series of operations. So first of all data, all variables are stored in registers. So what happens in data path is you add the contents of 2 registers and move it to a different register X. Or you multiply the contents of 2 registers Y and C and store it back in Y. Or you simply move the content of register D to register Z. So what is happening in data path is a series of what we call as register transfer operations. Things are moving from, data is moving from one register, one storage unit to another storage unit. And either simply going from one unit to the other, or after undergoing through some processing. Some arithmetic operation, some logical operation, something is going on, after which it is stored back here. And in what order things happen is all controlled by the controller. The controller decides, well, are you going to add a plus b and store it in x, or are you going to multiply y and c and store it in y, or are you going to simply move d to z? What really happens at in which clock cycle is all decided by the controller. So that's the brain deciding what happens in the data path here. All right, so that's the view of the digital system that we are building. The digital system now consists of data moving from one register to the other and undergoing processing. All right, so I was telling that, for example, if we are thinking of the data path controller view of the digital system, the data path that you see here, an example of a data path is here. The data path, as we can imagine, will consist of storage units, the registers, where we store the data. It consists of functional units, the adders and the multipliers and all the other things that you use for processing the data here. And then you have to interconnect them. You have to interconnect the registers, you have to interconnect the adders, multipliers, all of them together. So you need interconnect could be simply wires. A set of wires could be called a bus, or it could be multiplexers. We have used a lot of multiplexers in this particular view here. So this data path consists of these three broad elements here: data storage, functional units, and interconnect units. And the controller is our finite state machine. The controller is a finite state machine, goes through a series of states. In each state, it sends signals here to the data path, telling data path what to do, what to add, what to subtract, what to multiply. So the controller is sending all these data there and deciding what really happens in the data path. Now, the data path also sends the signal back to the controller, because many times this, you need to decide, should I do an addition or a subtraction, depending on some data which is stored here. So some signals are sent back to the controller as well to help the controller decide what to do next, which state to go and which operation to do. So there's a back and forth communication between data path and controller. So controller is our finite state machine that we just discussed, going through a series of states, sending signals back and forth. Now, before we, I think multiplexers, I'll just come to registers, maybe something that you're familiar with, but let me just remind you. So we need storage units. Storage units means we need memory. The simplest memory that you're familiar with is a D flip-flop. A single D flip-flop, when a clock comes, whatever is the signal here gets latched into this particular one. Now, in order to construct a register, what we can do is we can take a D flip-flop, add a 2:1 mux here, and add a load signal, let's say. So what happens is, if the load is 0, whatever is Q goes here and appears over here. So nothing really, the state of the system doesn't change. Whatever is Q, whatever is the data stored in this particular flip-flop stays there. But if you put a load equal to 1, then whatever comes external input then goes here and then gets stored here. Right? So the basic D flip-flop has been modified in this manner here. Now if you take several of these units and you connect them all up, then what you end up with, and the load signal is common to all of them. So what you end up with is what we call as a register. This is a 4-bit register. So if I put a load equal to 0, then the register maintains its state. Whatever was stored there, it still remains there. But if I put load equal to 1, then when the next clock cycle comes, whatever data I put here, it gets latched into my D flip-flop. So that's basically a register. A set of flip-flops with a mux may be there to decide what gets loaded and when it doesn't get loaded. Now I can take this register. So note that from a flip-flop, we have taken a set of flip-flops and made a register. I can take a set of registers and make what is called as a register file, a file of registers. So this is a file of several such registers have been taken. They've all been combined together. All of them have the same load signal. All of them have the same clock. But then what happens is I now give an address. Because I have several registers, now when I want to load a data into a particular register, which register does it go into? So I give an address. For example, I have 4 registers in it. And so I have a data bus, an address bus, which is 2 bits. So if it is 00, inside I will have a decoder. So if I put 00, it will enable the load line of a particular register, and the address will get, the data will get loaded into that particular one. If I put 01, it may get loaded here. If I put 0, whatever 10 and all that, it will get loaded. Similarly, what appears at the output would again be decided by the address bus. Whether the data outside is of this particular data which is being outputted is of this particular register, this one, or this one, depends on the address. So I can take several registers, combine them, and make a register file. If I expand this particular view, eventually we arrive at a memory, where, for example, the input and the output are all shared on one particular set of lines, which we call as the data bus. And then we have an address, we have read, write, and clock. So if you want to write the data into the memory, you apply a particular address and you enable the write line here. Depending on the address, one particular set of, let's say, registers selected, and the data is written into it. Or if you want to read, then the same set of lines are used to read the, we'll discuss these things in more detail later on. So what I'm pointing out is, starting from a single flip-flop, you can go to a register, you can go to a register file, or you can go a large-scale memory also. Now the way, don't think that the way all the memories are implemented is in the form of flip-flops. Registers are implemented in the form of flip-flops, but when you go to larger memories, the flip-flop becomes very inefficient. There are simpler ways of implementing large-scale memories. You may have heard of SRAM and DRAM, dynamic RAM and static RAM and all that. So when you go to large-scale memories, then you use a different way of implementing the storage elements. But for registers, the simple way of doing that is a flip-flop. So that's a brief introduction. We are talking about storage units, so brief introduction to what the storage units are. They can range from one flip-flop all the way to a large-scale memory. All right. So now the as I said, the way we will go and design a digital system is, at the highest level, you would be given some description of, for example, what you need to compute, right? So it's some behavioral description of what you're wanting to, the kind of computation. I'll give you an example, the kind of computation that you want to do. And what we need to do is, from the behavioral description, whatever description of the problem is, we want to generate a RTL view of the system here. So remember earlier I was saying that whatever is the description of the problem, you map it onto a state transition graph, and then you design your final state machine. Now I'm saying whatever is the description of your system, you map it onto a data path controller kind of an architecture. And then once you have a data path controller kind of architecture, if you recall, the elements of data path and controller are adders, subtractors, registers, and things like that. You synthesize that, and then you arrive at a gate view of the whole digital system at the gate level description here. So this is an RTL level description here, where you're only talking in terms of registers and how it goes from one register to the other. And this is some higher level description of what is it that you want to do. Okay. And so this is here. So let's take a very simple example. Let's say this is the thing that I want to do. A very, very simple, not a very useful computation maybe, but this is what I want to do. So while normally I can put a condition that if this is true, then do it. So while no condition is specified, and you have to continuously do it in a loop. So what you do is, so my system has data ABCD. So you read ABCD, and then you add A plus B plus C plus D, and you output it at Y. And then you go back again, read again, and you keep on doing it. So all that you're doing is you're reading this data that is there, you're adding them all up, and you're outputting it, right? And continuously you're doing it. That's what the system is supposed to do. And the data is a synchronous system, which means that data is coming, in sync with the clock. So there is a clock in my system. All the data comes in sync with the clock. The output is generated in sync with the clock. Everything that happens inside the system, everything is in sync with the clock. At some later point of time, we'll discuss synchronous sequential circuits versus asynchronous. The advantages, disadvantages. Most of the circuits are synchronous. Everything takes place in sync with a particular clock. All right, so it synchronizes all operations inside my system. All right, so this is what I want to do. This is the high-level view of what I'm looking for. Now, what do I want to do? I want to generate an RTL view of this particular system. I want to synthesize this and generate an RTL view. Now, what is an RTL view? If you remember, RTL view is, I want to tell, is described in terms of registers. So one way of describing, so I want a data path controller view of now this. I want to transform this description into a certain data path and a certain controller. So RTL is a clock cycle by clock cycle description of how I'm going to carry out this computation. Clock cycle by clock cycle description of how this is being done. For example, I may do it like this. I may have a state S0. So my system will go through a series of states. In some case, in very simple case, it may happen that whatever you have to do, you can do it in just one state. But in more, realistic cases, you'll have to go through several states, and then finish the entire computation. So y equal to a plus b plus c plus d. So what I'm going to do is my system is in S0 state. And what I do is I have registers R1, R2, R3, R4, and I read the data into my internal registers. A goes to R1, B goes to R2, C goes to R3, D goes to this. So I'm reading the data in this particular state. Next, in state S1, the contents of R1 and R2 are added together and put into a new register R5. So what I've done is A plus B is put into this. In the next case, the same R5 is taken and I add to it C. And the content is put back here. And in the next state, I add the contents of R5 plus R4 and I put it back here. And at the end, you can see here, I have the data available, which is 1. And then because it's in a loop, I go back to the first zeroth state here. And then it reads again a new set of data. Again, it does this and this, this and this. And, okay. Now, at this stage, there may be different ways of doing it. Okay. For example, I could have done R5, which will show R1 plus R2. And in the same state, I could have used another register R6 and added R3 plus R4 also. I could have done that also. So there may be, note that in every design, there will be many alternatives. So the issue is how do I evaluate the different alternatives? One of the issues is always there is how fast can my system run? The other issue is always how much area does my system occupy? Right? Area and delay and now increasingly power. These three elements are always there at the back of our mind. I want to minimize area. I want to maximize the performance, the frequency. Since this is a clock system, I want to maximize the clock frequency. And I want to minimize the power. So as far as the frequency and delay are concerned, just want to add at this stage two delays that you hear of. One is what we call as latency. The other one is what we call as throughput. So latency basically says, if I apply an X here, input to my system, after how much time the output is available, which corresponds to this particular input. Simple. The delay that it goes through, and after how much time does Z appear corresponding to this particular input, X that I've applied here. So that's the latency. All these systems are clocked systems, synchronous clocked systems here. The throughput is the rate at which input can be read. The rate at which input can be read is what we call as throughput. Now, let me, throughput and latency, let me describe. You can see the differences that come in. Let's say I have a picture here. I've not shown a input storage here and output storage here. So let's say I have a system like this, X. And let's put some delay values here, 0.5, 0.5, 0.5, 0.5. Okay. So if I apply at time t equal to 0 an input here, X, after how much time will the output appear? Worst case that we see each gate has 0.5, so it will appear after how much time? 2 nanoseconds. So the delay that my data goes through is 2 nanoseconds. Latency is 2 nanoseconds. At what rate can I refresh my data? If I apply at t equal to 0, my data, after how much time can I apply the next set of data? 2 nanoseconds. So the rate at which I can read my data or the rate at which I can process my data is also 2 nanoseconds. So my latency is 2 nanoseconds, throughput is 2 nanoseconds. But now take this particular system and let's suppose I break it up here at this particular part. I break it up and I add some storage elements like this. Okay, I've broken it up and I've added, I'm doing a temporary storage internal. And then, so again, 0.5, 0.5 here. So if I apply a data here, for the time being, let's assume that the flip-flops are zero delay. Zero delay, ideal, storage elements. Let's not get into the how much delay is there, just for the time being, okay? So if I apply a data here, after how much time will the output appear here? After how much time? Assuming that these are zero delays. 2 nanoseconds. It has to go through this, and it has to go through this 2 nanosecond. Latency is how much? 2 nanoseconds. At what rate can I refresh the data? Can you see that if I apply input here, after 1 nanosecond, it gets latched here, the intermediate outputs. And then it's available for further processing. And then I can read a new set of data after 1 nanosecond. right? So what is my throughput? 1 nanosecond. I can read the data every 1 nanosecond. Although the output corresponding to that data still appears after 2 nanoseconds. So what you can see is that I have a throughput of 1 nanosecond. I have a much higher clock rate. Throughput means at every 1 nanosecond I can read my new input. Okay, so throughput is 1 nanosecond. Latency is still 2 nanoseconds. Okay, so there are two kinds of delays that we keep on talking about. How much is the latency in my system and what is the throughput of my system? So what we are talking about is, what we did in here is that normal processing that was taking place, I chopped it up into this, and while this part is processing xn, the second part is processing xn minus 1, another part is processing xn minus 2, and the other part is processing xn minus 3. So this is what we called as pipelined processing. Instead of letting a data go in, and then after all the computation is over, then you read the next data, that's not an efficient process here. So what has been done is the system has been divided into several parts, and in sort of you can see that there's a pipeline here. This is processing n minus 3, n minus 2, n minus 1. Okay, and so often in many of the digital systems that you'll find, we do it in this particular manner. They are pipeline systems. Deliberately, the computation is broken into different parts in order to increase the throughput. Latency is still, in fact, if you go back and look at it, there's a cost associated with introducing the flip-flops here. And the flip-flops will have a delay. So invariably what happens is if the latency was 2 nanosecond, the latency here will increase because of the additional flip-flop delay here. So the latency will increase, but throughput will improve. So there's a price that you're paying, increase in latency, increased area because of the additional flip-flops, but the throughput becomes higher. You can read the data at a higher rate here. Anyway, so that's with respect to yes.
Sir, in the diagram, the storage element is placed one level even before, then the throughput will become 0.5.
Which one? Here?
Yeah.
No, here I said I already have, when I read the data, I already have storage elements. I already have storage elements.
In the second diagram, you play on this previous slide.
Yeah. Oh, if you break it up here?
Yeah.
Oh, well, you can do. That's what I'm saying. Here I've broken it into four stages.
Then your throughput will be like even half of that.
Well, no. So this is the point. Here, let's say in this example, let's say the flip-flop delay is flip-flop delay also you have to take into account, right? Flip-flop delay is not 0. So after a while, if you break it further, then you're not getting so much improvement. The flip-flop delay comes into picture here.
Instead of placing it after 1 nanosecond, what will happen if you place it after 0?
Oh, you're saying the same flip-flop, yes. If I place it here.
Yeah.
Okay, so this, now remember how did we calculate the clock rate? How did we calculate the clock rate? So what he's saying is if I take this and place it here at this particular point. Yes, for this, I can run the clock rate at 0.5 nanosecond, but what about from here to the here? 1.5. It's the same clock which is running everywhere. So you can't do that. It will still run at 1.5 nanosecond. Okay, so you remember, everything is clocked. There's a set of register here, there's a set of register here, there's a set of register here. So you're always going from one storage to the next storage. You're always going from there. So if you break it up here, you can easily see that from here to here, I have 1.5 nanosecond. I can't run my clock at 0.5 nanosecond. Okay. So this is a description that we had obtained. We had said that the complex computation that we had talked about, we're going to carry it out in these 4 states here, S0, S1, S2, S3. And now once we obtain this particular picture, then we can draw the structural view of my RTL, which is I can draw the data path. How do I draw the data path? Well, all the registers that are there that you see here, we just put R1, R2, R3, R4 and all that. All the registers are put. Each one of them has a load signal here. LD1, LD5, LD1, and so on and so forth. Each register has a load signal here. And note that A is going to go into R1, so A I put here. B is going to go into R2, I put here. C and D accordingly. Okay. So I, from this description, I know what are the registers in my system. So I put all of that here. I know, so data path is what? Storage units, functional units, and interconnect. right? What are the functional units? What do I have to do? Addition. How many adders do I need? How many adders? In this clock cycle, I'm using an adder. In the next state, I'm using an adder. In the next state, do I need 3 adders? 1 adder. 1 adder, so I put 1 adder here. Okay. Now I have to interconnect them up. Note that addition sometimes is taking place from R1 and R2. So the same adder is being used for this operation, and this operation. All right, so how do I do that? See if it makes sense. I use a multiplexer. And so fine, you can see here, if I want to carry this out, what do I have to do? Select signal should be such that I choose R1. I choose R1 and R1 goes here and then appears here. And similarly, I want to do this, so select signal should be such that R2 propagates here and comes over here. So whatever select signal 0, 0 or 0, 1 or whatever I have to apply such that R2 is routed to this particular input here, right? And then it gets added up and appears over here. In this case, similarly, the select signal has to be appropriately applied and the select signals have to be appropriately applied. So the appropriate data appears here and gets added here. And who's going to decide which select signal, where is going to come? From the controller. The controller will say, in this particular state, send this particular select signal. And so that is what will happen in the data path here. So now so remember, so from the problem description, I have to determine this particular picture of my design. I have to take whatever problem is at hand and I have to transform it into a state-by-state description of what happens in each particular state. So the complex computation that we were saying has to be broken into, these simple elementary computational steps. And I have to say what happens in each particular state. Once I have this particular view, it's rather straightforward, as you can see here. Once I have this particular view, to map it onto this. It's just a question of how many registers are there, what muxes are there, what adders and all that. And from there, then from this particular view, we can derive now. Now, before that, note that we said that we all wanted to use 1 adder. We all wanted to use 1 adder, but then there's a price that you have to pay. If you use 1 adder and it's shared amongst the different registers, you have to introduce muxes, right, to this thing. So there's a price that you have to pay. Why are we willing to pay that particular price? Well, you can see here. This is a 2:1 mux, just 2 bits here and a select input. Look at the cost associated with this mux, 5 micron by 5.3 micron, right? This is a mux here. This is a simple adder, 1-bit adder, full adder. What is the cost associated with this? 5 into 13.9. Adder is a much more expensive unit. And by the way, this is a very simple adder. If I have a more complex adder, like carry select adders and all that, the cost is even higher for each bit of addition, area cost. So adders are much more expensive than the multiplexers here. So we would like to economize on adders and liberally use the multiplexers. Okay, so that's why we didn't use multiple adders. If we had used multiple adders, we wouldn't have required the all these muxes then, that many muxes. Okay, but muxes are cheaper, and we would like to use that. Adders are more expensive. All right, so this is what we have now. All right, so we had obtained this description, and from this description, we had said we had mapped it onto this data path. And what do we need now? We need the controllers. The controller is a finite state machine, S0 to S1 to. We know that it's going from S0, S1, S2, S3. But the controller's description is not complete. In this case, the controller doesn't have any input. It doesn't receive any input from the data path. It just simply goes S0, S1, S2, S3 and back. It just keeps on cycling. It's more like a counter. It just goes 0, 0, 0, 0, 0, 1, keeps on counting and back. It's more like that. But what I need to do is I need to specify the outputs. The controller has to send outputs. So what outputs should it send? In S0, what should it send? It has to send outputs. So at each state, I have to define what the outputs are. So what should be the output of the controller? Let's see. Controller goes from S0 to S1 state. Does it, I have to load the signals here. right? Low R1, R2, R3, R4. So the load signals are enabled, LD1, 1, 1, and all that, enabled. I'm not loading anything in R5, so it is 0. The select signals don't matter. I'm not concerned about the select maybe. Then when I'm going from S1 to S2, whatever I enable. See, what did I tell you? Once the first clock edge comes, where is my system? In S0 state. I'm modeling my system as a Moore machine, not as a Mealy machine, as a Moore machine, okay? So my outputs depend only on the state. In this state, the outputs should be there. In this state, some outputs are there, in this state and all that. So by looking at the operation that has to take place in the different clock cycles, you have to decide what these different select signals are, all the load signals that you see here, all the outputs of the Moore machine are, all the load signals that you see here, and all the select signals of the muxes here. So those are the outputs of the Moore machine. So looking at now which operation has to take place, you have to decide what the values of LD to L5 and select signals are. And you put appropriate values. Right? So now the specification of the Moore machine is complete. I know the states that are there, and I know the output in each particular state. So we've already seen how to take this finite state machine and synthesize it. So we can synthesize this finite state machine, and we know how to make, let's say, flip-flops, and so in principle, how to make registers. Later on in the course, we'll quickly see how to make muxes and adders and all that. These are well-known units. So in principle, then the design is complete. These are very well-known units. Once you synthesize it, these are well-known units here. You can take their designs and put them all together, and at least you can obtain design at the gate level. You can obtain a gate level view of a system which will execute the operation y equal to a plus b plus c plus d continuously, right? So, all right. How do I decide the clock period? At what clock period can I run my system? Well, we've already seen. You have to see how the data goes from one register to the next register. So we have to see clock to queue delay, mux delay, adder delay, setup time, all of that we saw in the last lecture. You have to look at the worst case path through the data path, worst case or critical path, and then add up all the delays. And that will decide your what is the clock rate at which you can run the system. All right. So this is the view that we had obtained. We have said, given this particular problem, break it up into individual register transfer level operations and schedule them into different states here. Now, can I do that also? As we said, this is another alternative. Is that possible? I can take the same description and now talk about carrying that particular computation like this: S0, S1, S2. What is the difference between the two? Two adders, but what do I gain? By the way, what is the latency here? How many clock cycles? And what is the throughput? What is the throughput? Throughput means how often am I reading the data? No, I'm reading the data only in this. I'm reading the data here, and after how much time will I read the data again? Here. I'm reading the data after I do this and this and this and this, then I'm reading the data. So I'm reading it here. So 4. What about here? I need 3. So I need latency is 3. 3 states I'm using to carry out the computation. But the price that I have to pay is 2 adders. Can I do this also? Can I do this? Yes or no? Okay, think about it. All right. So I'll leave you with this. Can I take this and say that I can do it in 2 states, S0 and S1? Okay, think about what will happen here. Okay, so the view that we had just said was we are modeling a digital system as a data path controller architecture. When we add, lots of memory, there is of course memory in the data path, registers and all that, but that memory is very small. When we add lots of memory to it and there's a strong interaction between this data path controller with a memory, we eventually arrive at a microprocessor. So the view of a microprocessor is also that a microprocessor has a data path, has a controller, and it has a large memory through which the interaction takes place. And the microprocessor control also goes through a series of steps, keeps on executing elementary instructions and doing the computation. Let me give you an example. This is an 8085 microprocessor, very early microprocessor, is still widely taught. So I'm not going to go into the details of this particular microprocessor, but the broad elements of the microprocessor are given here. Now, what I want to show you is the following. You can see here, arithmetic logic unit. That's the place, we talked about, if you think of a data path, what do you have? A functional unit, an arithmetic unit and all that. So that's what it is, arithmetic logic unit. It can carry arithmetic operations and logical operations and all that. So data path will have that arithmetic logic unit here. All these that you see here are storage elements, registers, basically set of registers, right? And all this here are the control part, control unit. So when you look at the microprocessor inside, what do you see? You see the same thing, a functional unit, arithmetic logic unit. You see a bunch of registers that are there, and you see control logic. That's it. So that's what in general, that's what a microprocessor also is. So except that, of course, in principle that's what it is, but in practice, things are a lot more complicated here. So what I want to point out is this RTL architecture that we are talking about is very general. You can use it to describe a complete microprocessor as well. All right. So RTL describes clock by clock description of the system, right? Clock cycle by clock cycle, you have to describe how the computation is carried out. And as we just said, the complex computation, whatever we want to do, we want to break it up into elementary computations that can be carried out in a single clock cycle. As a first step, we may want to do the complex computation is described in terms of single assignment statements, meaning that a variable is assigned only once. So what I'm saying is the following. See, this description that you see here, what we obtained from this to this here, it can be done sort of intuitively. I look at this particular description and I say, well, okay, in state S0, I will do this. And then in state S1, I will do this, and S2 and all that. So we can do that intuitively, looking at a problem and break up the computation, assign it to different states, and put together by the way, did I write it here? Or I've not given here. So we have said that this is finite state machine. We said it goes from one state to the next. This has a name called algorithmic state machine, ASM. Instead of FSM that we had earlier, that FSM has evolved into an ASM, algorithmic state machine. So we have an algorithm which we have broken it down into how the algorithm is carried out in different states there. So FSM has evolved into ASM here. So what I'm saying is that I can take this description and I can get this particular ASM description in an intuitive manner by looking at it and deciding what to do, what and all. Or there can be a more formal method, a more formal series of steps that I go through and then arrive at this particular description. Now, the reason why we want to do a more and more formal ways of doing it, because once you come up with a very well-defined formal method of doing it, then you know what we'll do? We'll automate it. So the whole quest in digital design is that as much as possible, automate it. All right. So once you come up with a well-defined method, you can write a code, and maybe then all that you can do is you can write this description, and then there is a synthesis tool which will produce this for you, and which will produce the complete artwork. But most of the time, I think the synthesis tools are not so advanced that they can do this very well. So designers typically are manually involved in looking at what needs to be done and mapping it out into the different states that things have to be done. Okay. So a more formal way is what I'm saying is what we can do is the following. We can take this, let's say, the complex computation that is there here, A plus B plus C plus D, and I can break it up into elementary first computational steps. I can say, well, x1 is a plus b, x2 is x1 plus c, y is x2 plus d. I can break it up. Or I can break it up like this also. x1 is a plus b, x2 is c plus d, y is x1 plus c. Okay, I can do that. The next thing that you would see is I construct a data flow graph, how the data flows. So the same thing, I just denoted pictorially. A plus b, there's an operation v1, addition operation gives x1. x1 added with c produces x2. x2 added with d produces y. And there's an operation v1, v2, v3. So whatever was the original description, I've described it in terms of a data flow graph. Next thing is, I decide how these operations are going to take place in different clock cycles. So data flow graph, now I say I divide this into, I say, well, this is going to take place in one clock cycle. This is going to take place in the next clock cycle. And this is going to take place in the third clock cycle. So I'm scheduling the operation v1, v2, v3 in different clock cycles. Okay. Once you do that, then, from here, then you can try and obtain the ASM chart there. Okay. So taking a complex computation, breaking up into elementary computations, maybe constructing a graph, a data flow graph, how the data flows, and then deciding when am I going to do different elementary, different clock cycles. Now, different ways of, and now the scheduling. So you're scheduling the operations. The scheduling the operations could be constrained by timing, could be constrained by resource. For example, in some cases, you may try and do, let's say, schedule the operation v1, this addition, and this v2 in the same clock cycle. If you try to do that, you'll require 2 adders. If you try to, in this case, it cannot be done. The way it is written is, this depends on this way, right? Cannot be done. But let's suppose C and D, you were doing it here. So you would have required 2 adders. So scheduling can be resource constraint. I may have a finite resources. I have only 1 adder available. Right? I have only 1 adder available. So now I have to decide how to schedule my different operations. Or I may have a timing constraint. My timing may be very, very timing constraint in the sense that is given that the clock period should be, a certain value. Now note that I may even combine the 2 operations and try and do it in the same clock cycle. So there are different ways of doing it. Okay. So what we are trying to say is that to arrive at that ASM chart, algorithmic state machine description here, we have to do these kinds of steps. Either we do it intuitively, we look at it and we decide this is going to happen this and this is going to happen, this operation is going to happen in this clock cycle. Either we do it intuitively or we do it in a more formal manner of breaking it up into elementary steps, constructing a graph, scheduling it, and looking at what are the different options. So we'll just briefly go through in the next lecture what are the, how we carry this process in a slightly more formal manner. Okay? All right, so let's stop here.